Hello and welcome to everyone for joining this joint webinar hosted by Cisco and Telestream on Mastering PTP Network Resilience for SMPTE 2110 workflows. Let me first introduce Chris Lapp from Cisco, who will be presenting with me today. Hello, Chris.
Hey, Mike. My name's Chris. I'm a Technical Solutions Engineer at Cisco in the Media and Entertainment Group. I cover everything from SMPTE ST2110, AS67, any other flavor of media over IP across all Cisco technology.
And my name is Mike Waidson, and I'm an Application Engineer here at Telestream, supporting the video test solutions. Both of us will be your guides through this presentation on PTP. A few housekeeping items before we get started. There are a set of interactive tools that are in the upper right of the player. Just hover over this area for these icons to appear. You'll also find the Q&A window, where you can submit your questions. We'll do our best to answer your questions today, but if we don't get time to answer all of the questions, we'll respond via email to provide an answer to your question. For the best viewing experience today, we recommend using a wired connection and closing any non-essential programs running on your PC. The Sherpa platform will base the overall viewing quality on the bandwidth and resources available, and we want you to have the best overall experience. We are streaming this webinar today, so for the best audio, make sure to have your speakers or headphones adjusted to a suitable, comfortable listening level. It is preferred to use a Chrome browser, but if you have any problems with streaming of today's webinar, then please clear your cache and reset the browser, or try a different browser if necessary. A video on-demand version of the presentation will be available after the session via the same link that we used today. In this presentation, we'll discuss Precision Time Protocol and take a look at the standards that are an integral part of PTP for the SMPTE 2110 IP Media Network. We'll discuss the several message types that are used for communication in PTP and the types of clocks that can be used. There are several ways that the messages traverse the media network, so we'll examine the various communication models. Then we'll discuss the network topology that can be deployed and look at how to test the network. So Chris is going to start by discussing what is Precision Time Protocol.
So Precision Time Protocol, or IEEE 1588, it's a high precision distributed time and frequency synchronization protocol for packet networks, such as Ethernet, UDP, or IPv4. It has a client-server architecture. We call those PTP leaders and PTP followers. It primarily uses hardware timestamping to provide significantly better accuracy. This can be to the nanosecond or to the sub-microsecond, and it's much better than NTP. It has a very low administrative effort, and it's easy to manage and maintain as long as it's done properly. It can be low cost, it has low resource utilization on the network, and it can be used for high or low-end devices. It does have built-in redundancy and fault tolerance, and it's message-based. It has very limited bandwidth for the actual packets, but those messages can be very large in numbers. There's been 3 versions of this protocol so far. So in 2002, we had IEEE 1588-2002, otherwise known as PTP version 1. Then in 2008, PTP version 2 came out, and then we recently had another update in 2019, which we call PTP version 2.1. You might run into 3 different layers where these messages might exist at. So at layer 2, or Ethernet-based messaging, that's typically these days going to be seen in the telco mobile world. We don't use that in SMPTE ST2110, but for your knowledge, we put it here anyway. In the PTP world for 2110, typically we see the PTP messages at multicast addresses 224.0.1.129 and 224.0.0.107. And then in layer 4, we also have our UDP ports, UDP 319 and 320. Now, why do we need PTP? Well, at the end of the day, all of our media over IP devices must be clocked together. And when I say clocked together, that could be a sender and a receiver just simply doing some peer-to-peer clocking, or that could be a many-to-many type clocking. that clocking could be achieved through frame buffers or through synchronization through clocks, like what we do with PTP. What that does is it ensures that the origin timestamps, when they're sent, arrive at the destination and are assembled in the right order and thus play out with the right timing. If you have audio and video as separate signals, this is critical. Things like email and web pages, they don't care about all that, so that's why PTP is so niche to the media industry and a few other industries out there like financial trading. All modern media over IP solutions need some form of common reference clock to achieve synchronization. Again, this could be generally just done with frame buffers if you wanted to, or in some newer solutions out there, there's a peer-to-peer methodology for syncing the sender to the receiver, but that doesn't work in a many-to-many situation. So precision time protocol is the primary clock that we use here, although technically some of those standards out there do allow deviation from PTP itself. So as a simple comparison, software timestamping and hardware timestamping and why they're so different. So software timestamping is done at the application layer, and then the timestamps are generated there. It has to pass through the OS, through the MAC layer, through the physical layer, all the way before it transmits out. So that deviation, that jitter, that inaccuracy is pretty high. Although there are some PTP implementations that run in software, they're generally not very precise. With hardware timestamping, because we put those timestamps right in at that MAC physical layer, we have a much higher accuracy for those timestamps. They transit less time inside the host, so they are much more precise. So now I'm going to pass it off to Mike to talk a little bit about the standards in SMPTE ST2110 as they relate to PTP.
Thanks, Chris. Within some of the standards and devices, the terminology of master and slave has been used to denote the role of electronic devices within the system. The standards have been in the process of changing the terminology to use leader and follower, and we'll be using that for most of the presentation. But you'll find some technical papers, standards, and devices still use the old terminology. PTP is based on the IEEE 1588 standard for Precision Clock Synchronization Protocol for network measurement. This is the building block for how time is sent across the IP media network. This standard is used in a variety of applications for power grids, telecommunications, and of course broadcast applications. The use within a broadcast application are further defined by SMPTE 2059-1, which defines the SMPTE epoch, that is midnight on January the 1st, 1970, and outlines the alignment of video reference signals. SMPTE 2059-2, also referred to as the SMPTE profile, provides additional information on the carriage of specific broadcast data, such as time of day daily jam sync, daylight savings time, leap second, jump drop frame and color frame indication, along with communication models and further definitions for the requirements of PTP within broadcast applications. There is also an engineering guideline on PTP, e.g. 2059-10, and a recommended practice 2059-15 that provides a Yang data model to describe the syntax for PTP device monitoring. For audio, AES-67 standards define synchronization for audio devices using IEEE 1588, and there is an AES R16 report that provides recommendations for the harmonization of AES-67 and SMPTE 2059-2. Let's define some of the common terms and definitions used for PTP. Firstly, there is the grandmaster, which is the ultimate source of time for synchronization of PTP across the network. Next, we should define the leader clock, that is the source of time which all of the clocks on the path are synchronized to. Then the follower clock is typically synchronized to another clock within the PTP domain. The domain is a logical group of devices that synchronize to each other, but may not synchronize to another clock within another domain. The diagram illustrates a very basic topology of how these clocks would be connected together within different domains. There are a series of message types within PTP. Let's now take a look at these various message types and the information they contain. We'll start with the announce message, that establish the synchronization hierarchy in determining the Grand Master clock, using the Best Master Clock algorithm. We'll describe this process shortly. The announce message contains information on the domain priority 1 and priority 2 values, an indication of the clock class accuracy and variance, along with the clock ID, which is the MAC address of the device, and leap second information. Next, the sync message provides the value of time. This is a simple count of the number of seconds and nanoseconds since the empty epoch. Remember, that was January the 1st, 1970 at midnight. Additionally, in some cases, a follow-up message may be used in two-step mode. In this case, the time is carried within the follow-up message. For the moment, just be aware that there are two types of messages that can carry the time. We'll discuss the application for each different type as we go through the presentation. In PTP, we need to determine the time that the messages take to traverse the network, and this is done by sending messages between the follower and leader. Initially, a delay request message is sent by the follower to the leader. This contains a current timestamp of the device and the information on the device requesting the information. Once the leader receives the delay request, it should respond with a delay response, which provides information on the current timestamp of this device. From these messages, along with the sync message, the current time and one-way delay between the devices can be determined, and we'll show an explanation of how this works in a moment. The management message periodically finds information for SMPTE 2059. This message contains the TLV SMPTE metadata that contains the information on next and previous time jam, daylight savings time, and specific broadcast data like frame rate, drop frame, and color frame information. Signaling messages can be used to negotiate the message rates that can be handled between the leader and follower. If a peer delay mechanism is used, then P-delay request and P-delay response will be the message type used for forwarding and the reverse path communication between neighboring devices. P-delay is a more localized way of determining PTP time and offsets between localized devices rather than going back to the Grandmaster. Most IP media systems deployed so far have been end-to-end communication using delay request and response, so we'll focus primarily on this method today. But if you have questions on peer-to-peer, then please use the chat and Q&A to answer your question. Now, I'll ask Chris to explain the Best Master Clock algorithm and how that works.
Thanks, Mike. So the Best Master Clock algorithm, at the end of the day, needs to determine who should be the Grandmaster or the Master or the leader at that time, depending on which standard you're looking at the time. Now, the decision principles of this are primarily the priority 1 comes first. So Mike talked about that value of priority 1 that we're going to see in that announce message. So every device on the network that's participating in PTP has a priority 1 value. My typical sentiment for configuring this value on my Grandmaster is I'm going to typically set it at 10 on both my primary and my backup Grandmaster. The clock class and the clock accuracy and variance are all going to be a metric on that device itself at that time. So if it's locked to GPS, the class will be 6. If it's not locked to GPS, or if it's in holdover mode, it will be some other value. But typically that's going to be decided by the device itself. And then we come down to priority 2. Priority 2 is another usable configurable value. So my primary Grandmaster clock, if I've set my priority 1 as 10, I'm going to set this value to 10 on my primary master clock as well. On my secondary backup master clock, I would typically set this to 11 or some value after 10. That way I can know if all is good, I know exactly which Grandmaster is going to be in charge at that time. You could set them to 10 and 10, but then you're going to come down to tiebreakers and you might not necessarily know who's going to win that tiebreaker. Those tiebreakers could be the identifier, or it could be the identity of the sender or the receiver of that PTP message. Typically, identity of sender and identity of receiver come into play when we have multiple links between two devices and we need to decide which one of those links is going to be the PTP time link that we're going to use. The number of hops between the clock and the leader clock could also be used as a tiebreaker if all of those are equal. So if we look at the diagram here, we have an initial state, and in that state, we're going to be listening for announce messages. So we will listen for announce messages from a better leader, but if we don't see any announces from a better leader, we will become the leader on the network. But if we do see an announce from a better leader, we will let them become the leader and we will lock to them. That is roughly how the best master clock algorithm will work to decide who's going to be my grandmaster. So I think it would be fun to go between me and Mike and talk about a network situation where we're going to decide who is going to be the grandmaster at this situation. So Mike, could you tell me how you've configured the SPG 9000s in this situation?
Sure, Chris. So I've started with the SPGs in this system, and I've got 2 of those locked to GNSS, so they're synchronized to the sky. And I've defined one as primary and one as backup. So the SPG 9000 as a primary has a priority value of 10. And I've also set that priority value of 10 for the backup system as well. Through the network of switches, I have some media nodes down at the bottom, which are also SPG 9000s, and they might be providing reference to analog outputs and other digital reference signals. So they're locked to PTP. And I've also set their priority values to 10 for priority value number 1. Then the next round would be, since they're all equal in value and the lowest value wins, in this particular case, the first round is a draw and we can move to the next round. And the next round is the clock class, the clock accuracy, and the clock variance. And this is set by the device. So the device sets these parameters based on how it is locked. And so the value of clock class for devices that are locked to GNSS or GPS is 6. So those devices, primary and backup, will have a clock class of 6. The other devices that are locked to PTP may have a slightly higher value than clock class 6. If everything in the device also had a equal value of clock class 6, then we would go to the next round. And that's the priority 2 value that, again, the user gets to set. And so in this case, I've made my primary SPG have a priority value of 5, and my backup have a priority value of 10. And other devices along the network, I've decided on their priorities that with a slightly higher value. So in this particular case, because the priority 2 value lowest wins, that means the primary will be selected as the grandmaster in this case. And then, Chris, how would you configure the priority values for the switches within the network?
So for the switches, at the end of the day, we hope that the switch never has to take over for our primary and our backup grandmaster. We ideally want something that's locked to that GPS or GNSS to be in charge, but the switches have the ability to also be the leader in this case. So if we had some sort of critical failure, we need the switches to be able to hold time for a period of time until we get that GNSS signal back. So I personally like to have some deterministic way to know which switch is going to take over in that situation. So you'll see here I have 2 levels of boundary clock. I have that central boundary clock that both my clocks connect to, and I've configured priority 1 on this clock to be 128. On my other 2 layers of boundary clock, priority 1 on these 2 is 255. So that means if I have a failure of both my main and backup and the 2 SPGs at the bottom, that green boundary clock there is going to take over as the leader in the network, and the 2 other boundary clocks will lock to them. If I just left all as default config with 255 as priority 1, 255 as priority 2, then it would come down to the tiebreakers and ultimately end up probably being the MAC address of the switch that shows who it was. But because I don't probably know that offhand, I'm not going to be able to guess very quickly who is my grandmaster in that case. So I like to have some deterministic layering to the configuration of the switches.
Cool. There is another case where we might also decide to bypass those subsequent rounds and priority 2 values and just set the value for priority 1 to be the lowest. So rather than have every device kind of equal within the network of our active devices that we want to partake in the BMCA, we might decide to choose a lower value, let's say, for the primary. And so maybe we'll make that priority 1 value 5 instead of 10. Now in that case, if that was to happen, then in the first round, the lowest wins, and therefore the primary would win, and there'd be no need to go to the other rounds. So that would mean that we wouldn't care about what GNS was doing, we wouldn't care about the clock class, we wouldn't care about your priority 2 values that you'd set. You would have just basically decided this is going to be my grandmaster, and if this one fails, I'm going to choose the backup system, and that kind of process would then go through on the priority 1 value. So I'd choose different priority 1 values for my devices connected to the switch. So I make that decision on who I chose to be. That would be akin to what we do with an analog and SDI digital system for SPG, where the rack position typically denotes which is going to be the primary and which is going to be the backup, and that's set by the user, and that's done. And you could do that same way by using priority 1 as the value to set for your BMCA. If you have any questions, please use the Q&A section in the upper right corner. So now we have the mechanism for determining the grandmaster. Let's look at the message exchange that happens between a leader and a follower. Here we have a leader clock from the SPG 9000 that is sending messages to another media node, which is acting as a follower. At this stage, the leader and follower only know their own time, and the series of messages will enable us to determine the offset between the devices and the one-way delay. Firstly, the leader will send a sync message or a follow-up message with the timestamp, and will denote that value as T1. The message will make its way through the network and arrive at the follower at T2. Then the follower will send a delay request message at a time T3. Once this message traverses the network, it's received by the leader. Then a delay response should be sent at T4. When this message is received at the follower, it will have a series of time values, which can be used to determine the offset time between the leader time and the follower time, and then it should also be able to then make a slew to adjust that time difference, so that they are at the same time between the two devices. Or the device could perform a jam and move to the leader time immediately, but that may create a shock on the media node. The one-way delay can be calculated from the time from the leader to the follower and the time from the follower to the leader. And we simply divide by 2 to get the one-way path delay. So we have these simple calculations that we make to calculate that offset between the differences in these timestamp values of T1 to T4. And so that simple calculation can be used by the follower device to make these estimations of what the offset is between the two clocks and what the one-way delay is. Chris, are there any potential problems with the propagation of these messages?
There is, actually. So one of the things that PTP is famous for is working until it doesn't. And a lot of this happens to be because these following devices are sending those delay request messages. And they're destined for that leader or the grandmaster in that case in order to properly adjust the clock. However, what a lot of people don't know is because these are multicast messages, on the network side of things, we're going to do what's called a star comma G join of this multicast on everyone that's participating in PTP. That star comma G means that we're joining absolutely everyone participating in PTP, so that although my message coming from that following device is only destined for that device that's in charge, the grandmaster, everyone will receive my delay request message, even though they don't need it, and they will have to process it and they will have to discard it. And then when the grandmaster sends that delay response, he doesn't explicitly send it to me, he sends it out to the network and I absorb it. So it's again another multicast message that even though the devices don't need it, they'll have to absorb it and choose to discard it. And so this, although it's not a lot of bandwidth, it's time, right? So as we increase the number of devices on the network, it's a CPU task in order to take these messages in and discard the ones we don't need. And it can add actually to the delay that we're calculating because we have to process these messages and we have to discard them. And so it might not seem like a lot, but with roughly 100 devices on a network, if they're doing PTP at SMPTE rates, that's roughly 2,400 messages a second that those devices are going to have to deal with. Now, most media networks that I know of out there have more than 100 devices. So that message count can be very large and can be very taxing, especially to smaller scale devices. So it gets messy when there's PTP on the network. But we can solve this problem. So if we look at what we're going to do to solve this problem, the answer is boundary clocks. Now, there are two types of clocks that a network device can be, so a switch or a router. One is a boundary clock and one is a transparent clock, and both have their use cases. But when it comes to solving that scale problem and that message problem of PTP, boundary clock is the solution there. So if we look at how my PTP messages are going to traverse in the network here, if I'm coming from that grandmaster clock, that leader, my boundary clock is the actual follower. So those messages from that leader end at my boundary clock. The boundary clock will then generate new messages that head out of it towards the follower on the other side. So the relationship of those messages becomes interface to interface, essentially, in order to do the network. Now, a transparent clock, although it can compensate for delay in the network, it actually does not solve for that message flooding problem. It actually transports those messages on the data plane as regular multicast, versus in boundary clock, you can think of it as control plane messages on the network, no different than a PIM hello message or something like that, BFD messages. So at the end of the day, boundary clock solves that scale problem, and it's also best for the accuracy at the follower because it doesn't have to process a lot of those extra messages.
So there are recommended rates for each of the message types within PTP. In the switch configuration, these are written in the form of log to the base 2. So a value of 0 represents once per second, and a value of -3 equates to 8 times per second. The table shows the recommended value and the range of values in brackets for each of the standards. Typically, the announce message is sent once per second, and the sync, delay request, response are set to 8 messages per second. There is an announce timeout, and it's typically set to 3, so if the grandmaster stops responding after a period of 3 announce messages, then a BMCA process will be started for the next suitable grandmaster. The overall data rates, as Chris mentioned, for PTP may seem quite small when compared to video media transmission rates. But you have to remember that these rates can be multiplied by the number of media nodes within the system, and then the overall rates that the grandmaster has to respond to can become larger, with thousands of devices requiring PTP communication. Therefore, it's a good idea to constrain the traffic flow of PTP across the network by the use of boundary clock and other methods. One of those other methods is by using different communication models. So let's take a look. Just to outline the different types of communication that can happen within IP, firstly we have unicast, which is a one-to-one communication from one sender to one receiver. We have broadcast messages that are used to send out messages to all devices on the local area network. And then we can have multicast, which is a method of sending one stream to many devices that request to join the flow. For PTP, we typically use 224.0.1.129 as the multicast address, and all devices will join the stream to receive PTP. For PTP specifically, we also have a mixed SMPTE communication model that uses a combination of unicast and multicast for certain message types. So in this case, we decided that all devices will want to receive the announce, the sync, the follow-up, and management. So we'll send these as multicast messages. Now, then in those cases, we've got those sent to all devices. But there are certain other messages that we only need to send via unicast, and so that it will send delay requests and delay responses as a unicast, because that goes from one device directly back to the grandmaster and from the grandmaster back directly back to the device that's requesting that information. Now, Chris, you were telling us that SMPTE mix might not apply when we use a boundary clock.
Correct, yeah, because with boundary clock, we actually take that communication and make it interface to device or interface to interface. The benefit of that SMPTE mixed mode is now lost because we can actually just abstract that message load already at the boundary clock level. But without boundary clock, SMPTE mixed mode is a very good idea.
Chris, what is another way that we could prioritize traffic for QoS?
So for PTP, especially in non-PTP aware networks, we want to make sure that PTP is put at the front line of the network and always dequeued as the first thing on the interface. It gets all precedence. So within the network, we have QoS. So QoS has been around for a long time, and we'll typically put PTP into what we call the expedited forwarding queue. So that's very low loss, very low latency. The media, like the audio or the video, will typically fall in the queue after that. So we'll typically put that in assured forwarding. Very typically, I see audio in AF41, for example. Now, when you enable boundary clock, these QoS values actually no longer matter for the queuing through the actual switch. Because it becomes a control plane message, it's automatically going to be dequeued first before anything else. However, a lot of media devices out there actually use these DSCP tags that we use for QoS, so that once the device receives it, they need to use that tag to plop it into the right stack of packets inside their device. So even if you're using boundary clock, it's a good idea to maintain these tags in the network and forward them on to the media endpoints. But if you don't have boundary clock, rest assured you need to be putting PTP into that expedited forwarding queue.
Thanks, Chris.
No problem.
So that covers the major parts of the PTP standard and processes. Don't forget, if you have any questions, please use the Q&A section at the upper right corner. Now let's see how we would deploy PTP across our network and look at various topologies. Starting with an SPG 9000, where we have a primary and a backup system that each have GNS to lock as a reference. There are two PTP ports on the SPG 9000 that can be configured for 1G or 10G interfaces and connected to the switch that could be transparent or boundary clock mode. Therefore, you may want to be careful considering how to set the priority of these ports to control which one is active for the various fault conditions that might arise. If we consider a 2022-7 network with a primary and secondary network, then we may have an air gap between the two switches. And it would be a good idea if we have a PTP-only connection between those switches to ensure that the same GM is used across both networks. We can then use a boundary clock, in this case, to feed the rest of the network with PTP for the various switches and media nodes that may be in the system. Chris, can you perhaps show us some examples of network topologies that can be used?
Absolutely. So if we look at a very typical spine leaf, and in the IT world, when we say spine leaf, most often a spine leaf has at least two spines and some number of leaves. I know in the media world, sometimes we use a single spine, but let's look at that two spine system first. So in this case, we have our clocks, as Mike said, configured as primary and backup. And then I'm going to have my spines. And I would prefer to have both of those grandmasters dually connected to both sides of the network. So my primary goes both to spine 1 and spine 2. You could also technically connect them to leaves. It really depends on what interface speeds you have available. If your spine is only 400 gig, you might not be able to connect your clock there. So you might need to connect it at a leaf level, for example. But net, somewhere on that side, it needs to be connected to both the primary and the secondary. Wherever that connection exists, we are going to put that PTP-only connection between the two. As Mike said, the best preference, in my opinion, is to have the same grandmaster on both sides. So that way the failover between the two, if it has to happen, is actually a lot faster. And then towards the leaf side of things, we're going to have obviously spine A and spine B in this case, because it's a single system, not a redundant system, connected to that leaf, and same on the other side. And what you'll see is one of those links at that leaf layer have become what we call a passive interface. So that means that it's following on another port, and that passive interface, it sees the same grandmaster, but it won the election, but it sees the grandmaster that won the election through that same interface, and it can fail over there without doing a full election. And I then have my followers, which are connected to boundary clock ports, and they are followers as well. But if we move over to the redundant side of things in the 2022-7 world, here we have that same clock level, but as we start to expand out, we might need to build what we call at Cisco a PTP feeder layer, which could also technically be the network border. So typically in the IT world, we have these things called border routers, or maybe you call them a core router, something that connects all of your systems together, especially if you're going to be deploying multiple SMPTE 2110 systems that are all -7. You want to connect them all to the same clock. So you need some central location to do all that. So that's what we're going to do there. Again, that's connected by a PTP only link so that we can get that grandmaster to both sides. Then we have our spines. Here I have a red spine and a blue spine. And then I have my leaves on the other side as well. So you'll see here that my media leaves, I have a red one and a blue one. And on the follower side, it's following one side of the network. It could possibly be following both. So depending on the PTP implementation on your device, you might see both ports listed as follower, or you might see one port listed as follower, one port listed as passive. So it really depends on the PTP implementation that that device has, but both are options that we'll see out there. But the main thing here is that on my red side and my blue side, I see the same grandmaster, and I can fail over very easily between the two. As we start to move to what some people will call a hub-spoke system, or maybe a multi-site system, depending on how you want to look at it, because we don't use the old-style hub-spoke type networks for media anymore. Here, typically what we'll see is some kind of WAN or hub site, and the spokes are out some large distance or possibly connected via circuits, MPLS circuits, things like that. It's nearly impossible to send PTP from that hub out towards those spokes. Now, if you could guarantee that the delay from the hub to the spoke is the exact same one direction as it is the other direction, then you could technically send PTP across that connection. But that's very hard to do. There's typically going to be asymmetry on those connections. So what we need to do in this case is everything that we've just designed here for our redundant system, we'll need to deploy that at each site. So we'd have a GNSS connected clock at every site, so they're all traceable to the same time in order to get that PTP resiliency.
Thanks, Chris. Now let's take a look at testing methodologies we could use. So the underlying principles are fairly straightforward as you begin to understand the concepts involved. We should now consider how we can evaluate the PTP system so that we can better understand the system workflow. What happens when the PTP grandmaster is lost? Well, as we have mentioned, typically in the system, if the announce message is not received periodically, then a timeout would occur and the BMCA would be initiated to determine the next grandmaster. We might want to evaluate the failover in the network, so we might actually want to set up conditions where we can actually do this. And simply one of those to do would be to change the priority. So by changing the priority of one of the devices to make it then become the grandmaster and evaluate then what happens. We could also disconnect a cable from the grandmaster and see the results of the change. Or a device could be powered down to see the effect of the changeover on PTP failover. And in the 2022-7 case, we could power down one whole side of the network and then see what happens. It's important to understand what happens in each of these cases, so we can invaluably understand your system design and evaluate what happens in the various scenarios. How well do the switches and the media nodes cope with the change is very important within the system. Before you decide to implement, you should do these tests and then go live. Being able to troubleshoot issues within PTP can help you to isolate potential problems. These recommendations can be as simple as checking the domain value for the device and the network switch configuration across the network. Did someone connect a new device and wonder why it's not locked to PTP, only to find out that it has the default AES67 domain, and the domain being used within your network is different? It would be a good idea to know the grandmaster IDs that are the MAC addresses of your primary and backup SPG, along with the MAC addresses of the switches that are in the network, in order to help you determine which device is currently the grandmaster within the network. It can be important to check the message rates and are they configured appropriately for the media node, switches, and master clock across the network. Additionally, it can be useful to check the communication model and whether the device is operating in one-step or two-step mode. Devices like the SPG will show the information for each specific PTP instance and show the clock identity along with the device information, whether the device is active or passive. The device also shows the priority information along with the clock class and the clock accuracy. Note that active will mean that it is the grandmaster within the system currently, and if it showed passive, it indicates that it's not the current grandmaster but could become the next grandmaster if required. Chris, what are some of the metrics we can check in the switches?
So on the switches, the very first thing that you should understand is what is the status of the ports. Now, when you look at this command on the switch, show PTP brief, you're looking at the ports from the switch's perspective. So when it says it is a master or a leader port, that means that the switch is leading that port. When it says follower or slave, that means that that's the port that switch is getting time from. So it's important to understand that denotion. You should have multiple master ports, but only one following or slave port. We also provide a graphical view of this in our application NDFC, where we can see from the switch's perspective, what is the BMCA status of all the different ports at that exact moment in time. So purple here, you can see I have one port that's following, and then I have many other master ports and some passive ports. Just like the SPG, we can show what our ID is on the switch. So if you do show PTP clock, you can see what that switch's time is, what that switch's identity is, that switch's priority values, its class, its accuracy. But if we do show PTP parent, we will see who the grandmaster is on the system at that time. And ideally, show PTP parent shows your actual grandmaster. If it shows something else, this could indicate a problem. The main thing to look out for on this page here is that the offset for master and the mean path delay should be relatively consistent. They shouldn't be jumping up and down by very large values. Small values is fine because obviously the network is very packet based and things are traveling across those links, and we could see a small increase of 100 units here up and down. But if you see increases and decreases of over 1,000, things like that, that indicates that something's probably wrong. We can also see some of that same data in the Nexus dashboard application as well under the clock status page on the switches. Another thing that's useful on the switch is to look at the corrections. So obviously, we're doing the same delay request and delay response messages that the media following devices will be doing. So we can actually go into the switches and see what we're doing on those messages 8 times per second. We also track these values over time, so we can actually plot them in a graph and look at the mean path delay in a graph over time inside of Nexus dashboard as well. Here I've set my threshold to show any correction over 200 nanoseconds. Obviously 200 nanoseconds is a very small value, but you could set that to 500 and probably look at more realistic data that you might want to see. Another command that we can do is show PTP port interface. So although my global settings on the config might be showing exactly what I want, it could be that for some reason in the software, the port thinks it's doing something different. So we can actually go look at the data on the port itself to make sure that its domain is correct and it's advertising the right domain, making sure that it matches my global config on the switch and in my system. Things like the version as well, the port identity, you can get all of that information from the port. And one of the other most useful commands is show PTP counters. So show PTP counters, what you want to look for here, and especially in a SMPTE environment, is that the delay request and the delay response messages are the same number. For every delay response that I send, I should get for every delay request that I send, I should get a delay response. If those numbers don't match, then we probably have an issue communicating between those two devices. As well, the sync and follow-up probably should be relatively close to that as well, and the announce will be a little bit less. You can also see from here how many management messages you've gotten as well.
Thanks, Chris. Those are a set of useful commands that I often use for monitoring PTP. At the end of the chain, we have our media node that may be able to provide some metrics on monitoring of PTP. Here I'm showing the prism acting as a media node that is receiving PTP from a switch port and then viewing the syntax of the PTP within the IP session in the upper right. So I can confirm the grandmaster ID, the priority values, along with the message rates. Within Prism, also I can monitor graphically the leader to follower forward path or the reverse path follower to leader to hopefully see a relatively flat line for PTP. There's also in the top left the offset from leader, which is an average of the forward and reverse paths. You may notice a little spike in the graph showing a change that happened to PTP, perhaps a change in grandmaster ID, and you can see those plots of graph from 60-second window in this particular case up to a day, and so you'll be able to note the health of your PTP system, and this can be helpful in identifying changes within the network. We've only briefly looked at evaluating and testing, so we are planning another webinar on this subject after the summer break in the fall. Watch out for an email that will announce this in the coming months. We have covered the basics in this session discussing the PTP standards and syntax used. We've looked at the communication models and how these messages traverse the network in the topology. We've also shown how we would test the basics of PTP in the system. It's important to remember the basics in order to troubleshoot problems within your system. We've looked at those communication modes and the topologies that hopefully have given you some understanding of how PTP works. Now let's open it up to a few questions that we've had, and we'll start with one that's how many domains would we configure on the network, Chris?
So in a large media system, my preference would be to just have one domain for the entire network. And that would be whether it's a red system, a red-blue system, multiple red-blue systems. Ideally, my preference is everyone's locked to the same domain, and I feed everyone from the same set of network feeders or network borders so that they're all locked together. That makes it very simplistic for troubleshooting.
Good. I like to just use the one domain and not worry about anything else. Everything is set to the same particular piece, and I think it's a good idea if you don't use the defaults, which are 0 and 127 depending on it's audio or video. So we use a different value that's not those defaults, and the reason is if we put some new device on the network, it will use those defaults, and if it's not been configured, then we have to go in there and change those values to that specific piece. Now there are some particular applications like in mobile where they bring a whole load of trucks together, and so they tend to make the trucks all have the domain value of 127, so that it's more easy for them to interconnect between devices and trucks when they get together. So there are different ways, but I prefer to have a domain that's not a default. The next question is, when would you use a transparent clock over a boundary clock?
So my personal preference is always boundary clock, but there is a few use cases where transparent clock could be useful, such as at the very top layer of the network, it could provide a slightly faster failover between the primary and the backup. It could also be that maybe you don't have the ability to do boundary clock at that layer for whatever reason, and a transparent clock is good enough to adjust for those transient delays, so that's fine in that instance. But my preference is always boundary clock, but again, there is always the use case where a transparent clock could be useful. There are trade-offs between using either or. What's your thoughts, Mike?
So I prefer a boundary clock. It's a very good thing. It keeps the traffic low. It keeps my grandmaster not having to work too hard to process a lot of messages and just deal mainly with the switch connections between the grandmaster and the boundary clock. So boundary clock is a good thing to use in the system. There are some cases perhaps where if I'm trying to troubleshoot something, I might switch a device to a transparent clock because it then just lets the traffic process as an IP packet rather than creating that boundary between the two. So then I could check and see what's happening to the PTP messages within the system. So I might use it that way to kind of troubleshoot some things, but most of my applications revolve around using boundary clocks in the system. So another question we have, is it possible to have ABB and SMPTE 2110 serving PTP clocks?
So the short answer is no. So if you are using a switch as a clock, so a boundary clock or a transparent clock, that switch can only operate generally in one PTP mode at a time. It has a single oscillator. That oscillator knows its time, and it has a single PTP instance running in the software. So the difference here would be that AVB or 802.1 AS, it is its entirely own PTP profile and has its own standard associated with it. So the way that it communicates, for example, in a boundary clock method, is actually more akin to what we would consider in PTP version 2 a peer-to-peer transparent clock method. So although they both use the term boundary clock, they communicate in very different ways and in very different methods. So net-net is, if you are using PTP-aware networks, you cannot do both at the same time. Now you could, in theory, run a little piece of the network in AVB mode and then just pass multicast PTP messages across the network. But again, it's not going to be doing boundary clock for those messages.
Thanks, Chris. So what is the purpose of having that PTP connection between the path 1 and the path 2 of the redundant network?
So typically in a network, between a leaf and a spine, there's always going to be multiple connections because we're doing very high bandwidth media. So there's going to be sometimes 2, sometimes 6, sometimes 8, sometimes 12 connections between each switch. So there's going to be some election between those. So in that case, we're putting multiple links for aggregate bandwidth, and we're just going to run PTP boundary clock on all those interfaces. So there'll always be multiple interfaces there.
And we might just have time for one more question, which is, what is the difference between one-step and two-step?
Do you want to take this one, Mike?
Sure. So in this particular case, we're going to be dealing with primarily the cases of a device going end to end within the particular system. So in those particular parts, we are sending our sync message with the time information, and that sync message is being provided throughout the network within those particular pieces and going to the end devices. So there's one step of communication for the time information between those particular pieces. In the two-step mode, typically we might use that in a transparent clock kind of configuration. Then in those particular cases, we are going to send a sync message, but it will have typically no time information. And that message will allow us to determine through the devices in the network what the specific time is it takes for that message to go through the active device. When we get to that particular point, we'll know the time value. So we can add a correction factor in the follow-up message that will then allow us to add that value of the processing time it might take for the message to go through the device relative to queuing. So we'll send this correction value, we'll send it as a follow-up message, and now we then have a two-step process that is containing the time information. So that follow-up message is how we are basically providing the time this time and calculating it in some devices as a correction factor, so that we don't have to delay or do some other extra calculations in there. We'll use the sync to calculate that kind of correction value offset, and then at the end of the chain, the media node, it can use that information to calculate the overall offset and delay in the network by using the correction factor and all of those other T1 to T4 values. So that's the main difference between one-step and two-step.
I think it's important to note that one-step and two-step are compatible with each other, and you can have a device receive one-step and provide two-step on the other side, and vice versa. And there's some language about this in the standard as to what a device needs to support to be a follower and what a device needs to support to be a leader. There are specific conformance requirements for either way.
Great. That just about brings us to the end of this particular session. Thank you for joining us and for attending this webinar. If you want to review the content again, it will be available on demand shortly. You'll also find some valuable resources from Telestream and Cisco. We've published some white papers and technical briefs on the topic of PTP, and we'll send this in a follow-up email. Additionally, if you've had questions during today's webinar, we'll be compiling our responses and send that information out to you shortly too. We hope you'll join us for the next webinar in the fall, when we'll discuss PTP and how to deploy, test and monitor PTP in our IP media networks. Thank you all, and thank you, Chris, for joining me today. This concludes this presentation.
Thanks for having me, Mike.
Pleasure.